In this section, we are interested in graphing polynomial functions. Now, polynomial functions, we've discussed them before quite a bit. We talked about the zeros of polynomial functions. We talked about quadratic functions, linear functions before. So we are now going to look at more general and higher order polynomial functions. So our first objective is to actually look at the graph of a power function. So our power functions, these are functions that are in the form power function. As you can see, it's in the form f of x, x to the n, where n is at least 1. So I have x, x squared, x cubed, x fourth. These are the power functions in their simplest form, in that there's no shifts or any scaling effect on these polynomials, on these power functions. Remember, these power functions are polynomials. More specifically, they are monomials because there's only one term. Okay, so what does the graph of these look like? Well, we already know what the graph of x looks like. For example, this would be the graph of f of x equal x, or simply y equal x, right? We have seen the graph of quadratic function, the parabola, the simplest form, the basic parabola x squared. We have seen that one before. So what happens as the power increases for these polynomial functions? So what I have is I actually graph these for us. So let me just bring these up for you, and so you can see if we can generalize some interesting facts about these power functions. The one you're looking at on the left, this one, the one on the left side, for this one, if you note, let's see, the red one, this is the graph of y equal x squared. As the exponent increases, so we go from x squared to x to the fourth and x to the sixth, you can kind of see how the branch, the right left branch of the parabola closes in. And what happens also as this closes in, it causes this massive broadening effect, right? Or I should say widening effect around 0, which is the vertex. Now, if you note, all of these power functions, by the way, go through 0.11 in their basic form, that is without any shifts. See that? At point when x is 1, y is 1, and the same thing with this one. When x is 1, y is 1. All power functions go through 1, 1. And then in the case of odd powers, so what I have here to the right, I have x, and then this one is x cubed, and the red one is x to the fifth. So again, all of them go through 1, 1. If it's even, the exponent even, for even powers, it goes through -1, 1. And for odd powers, the graph goes through -1, -1. So keep in mind and try to kind of remember the patterns that you're seeing. As the exponent on x increases, no matter whether exponent is odd or even, you have this flattening or widening effect around the x-intercept. And of course, the x-intercept for all of these are at 0, 0. Okay, so we're going to keep this in mind as we graph the general polynomial functions later on. Okay, and notice that 0, x equals 0, happens to be a 0 of these functions. Again, that's without shifting them to the right or to the left. All right, now what about the general polynomial functions? So for the general, this is our second objective. For general polynomial functions, let's take a look at these. General polynomial functions. And what I have in mind is the hk form of the function. So I'm thinking about f of x in the form ax minus h. This would be to a power of n plus k. Remember, we were talking about power functions, so that's why I have n in the exponent. And I'm allowing for scaling it, horizontal shift, and I'm also allowing for vertical shift, of the basic graphs. Okay, now let's go through and determine the effect of each of these. If the number in front, the coefficient in front of the parentheses here in front of the function is negative, that causes a reflection across the x-axis. So we just simply get a reflection across x-axis. It simply flips the graph over. Okay, now if absolute value of a is greater than 1, we have a vertical stretch. Remember, we've done this before. Vertical stretch will give it that narrowing effect. Vertical stretch by a factor of a. And if absolute value of a is between 1 and 0, the reason we go absolute value is because if a is negative, we simply attribute negative to the reflection. So if the absolute value is between 0 and 1, then you have this vertical compression. And with vertical compression, you get this flattening effect or widening effect. So the vertical stretch will cause the graph to become narrower than what it used to. And for this one, it's going to be wider. The compression gives that visual impression that the graph is widening around. Most likely it's x-intercepts. Now, in terms of h, remember we've taken up hk form before. And just like before, if h is positive, then we have a horizontal shift. This time it will be to the right, h units. If h is less than 0, we still have the horizontal shift, except this time it will be to the left, absolute value of h units, because h is negative. So if it's negative 3, it moves left 3. The reason for absolute value is that. Okay, what about k? The effect of k is, if k is positive, then we have a vertical shift of the graph. So it's going to shift up k units. And if k is less than 0, then we have a vertical shift downward. Okay, so both of those are shifts, except positive you go up, negative the graph moves down. Absolute value of k units. So if k is negative 5, then the graph moves down 5 units, not negative 5 units. The down movement accounts for the negative. Okay, so that would be the second objective. This is the effect on the general power functions, on the polynomials. And our third objective was to look at the behaviors at 0, and we've kind of touched up on that right in here. We're talking about behavior at 0. So keep in mind, as the power increases, let me just make a note of this, as n increases. Remember, n is the power, the exponent on the power function. Increases, the graph becomes flatter near its intercept. And that would be the x-intercept near, let me just put the x-intercept. Okay, so for example, again, let's say I have x cubed and x to the 5th. If the x cubed function looks like this, x to the 5th will look more flat. There you have it. So this one is x to the 5th, and this one was x cubed. All right. So that would be the behavior, again, near the intercepts. If I have another example, let's say with the even function, suppose I have f of x is equal to x minus 2 to the 4th power. So for x minus 2 to the 4th, there's going to be a horizontal shift to the right of x to the 4th. Remember, x to the 4th is going to be very flat near, this is just x to the 4th, near flat near 0. And x minus 2, we'll shift it to the right 2 units, and then we have that very flat, almost parabolic, but it's really not a parabola, just to clarify. In fact, they don't even call it a parabola. Parabolas are only second degree functions. So there you go, x minus 2 to the 4th. Again, it's important to know the behavior at 0 of these polynomial functions. Now, let's talk about the turning points. Okay, this is objective number 4. Objective number 4 is the turning points of the graph of the polynomial functions, the turning points. So we can say in terms of the degree of the polynomial, an nth degree polynomial has at most n minus 1 turning points. We're talking again about the graphs of these functions, okay? And there you have it. So for example, for instance, suppose I have a function, let me make one up, f of x is equal to x plus 3 to the 5th power. Okay, well here the exponent is 5, so this could have at most 5 minus 1, which is 4 turning points. Doesn't have to, but it could have at most no more than that. Okay, so if I graph this one, quite likely the graph of this is going to look like that, like what I'm about to draw. And there you have it. This would be the graph of x plus 3 to the 5th. Notice in this case, there's actually the turning points. By the way, what are turning points? The turning point is where the graph changes from high to low, or from low going to high. This is where it's turning. It's where it changes from increasing to decreasing, or decreasing to increasing. Now if I trace this graph, notice I'm always increasing. So this graph that I have drawn has no turning points. This one has no turning point. But we would expect no more than 4. It doesn't mean it has to have 4. At most means that, or fewer. Okay. So for instance, let's say, just to make up a function here, suppose my function, I have f of x is x to the 4th, negative 3x plus 7. This is a 4th degree polynomial, so n is 4. This can have at most 3 turning points. Again, it may have only 2, but no more than 3. It could have only 1, it could have none, but no more than. Okay, now the next thing that we are interested in, we want to talk about the end behavior. So we're talking in item 4, turning points and end behavior. So we're still in objective number 4. Let's talk about the end behavior. When we talk about the end behavior, we're talking about a place where x gets very large, that's x going to infinity, means very large, or x approaching negative infinity. Those are the extremes for us. So as x goes to infinity, we want to know what is the behavior of the function, and as x approaches negative infinity, what is the behavior of the function? How is it going to behave? So the behavior, the extreme or the end behavior of a polynomial is determined by the coefficient on, and in fact the entire dominating term. So let's talk about what the dominating term is. The dominating term is actually the term of the highest degree in the polynomial. So this is the highest degree term in polynomial. So for instance, in example, let's say I have f of x is equal to x to the 5th minus 4x cubed plus 1000x squared, some unrealistic coefficient. we say that the leading term here is the fifth degree, right? The highest degree term is the fifth degree term, this one. So this pretty much dominates the end behavior. What it dominates is the end behavior of the polynomial. Okay. Another example, suppose I have x cubed negative 10,000x. Okay, and there we have that one. Now, to show you what I mean by dominating is this. If I let x be 10, small number, okay, well, f at 10, what is it going to look like for the cube function? So that's just going to be 1,000 minus 100,000, right? And the number is negative 99,000, right? Negative 99,000. So it looks like the second term is dominating because it has a massive coefficient, right? But what happens as x increases? Let's do f at 100. When x is 100, well, 100 cubed is 1,000,000, isn't it? That's x cubed. Negative 100 times 10,000 is also 1,000,000. So notice how the x cubed caught up to that x term. Now the difference is 0. And let's see, what if I have f evaluated at, I don't know, let's put 1,000, some crazy number. Well, the cube, x cubed, will cube 1,000, right? So now that's about 1,000,000,000. And the 100 changes to 1,000. So this is going to be 10,000 times 1,000, because remember x is 1,000. And this is going to be 1. You see how it's overtaking the linear term? Minus this one has only 7 zeros, 10 million. So we're now talking about now a positive gain of 990 million over the linear term, and that's just f at 1,000, not infinity. So this is what we're talking about dominating. The leading term, when polynomial is in descending powers, the leading term dominates the end behavior of the polynomial. So how are we going to show this on the graph, this dominating behavior? Okay, so let's say we're talking about now dominating term in the form ax to the n. Okay, now this dominating term, it depends on whether the exponent is odd or even. Okay, so when n is odd, so we're going to look at the case where n is odd. When n is odd, if a is positive, the leading term is positive. Okay, if n is odd and the coefficient on that term is positive, then as x gets very large, so does the function f. As x gets very small, so does the function f. Okay, and x cubed is a good example of this one to sort of remember this. But we want to show this in general. So suppose my third degree polynomial is going to look like this. Whatever it may do between 0 and whatever, the extreme behavior, this is what we're talking about. What's going to happen as x gets very large? Of course, on the graphs, we cannot show infinity, right? We can just conceptualize about it. So here's the example of n odd and a positive. So remember, the function rises very rapidly and it falls very rapidly also as the exponent is odd and as x increases. So there you go. This is the end behavior for very large x, and this is for very small x. All right. Now, what if the coefficient, is negative? We still look at n odd, except if the coefficient on the leading term is now negative. If the coefficient on the leading term is negative, then as x becomes very large, the function approaches negative infinity because of the negative in front of that term. And if x approaches negative infinity, then f approaches positive infinity. So how is this going to look like? Well, for a given power function of any odd function, not odd function, sorry, for any odd exponent. So it could be x to the 7th, x to the 10th, whatever. So the function again may do this, whatever it may do, but as x goes to infinity, this is the end behavior here and the end behavior on the negative side when x approaches negative infinity. So this is again reference to what we're talking about here. You see that? Of course, I got these backwards there. So x gets very large, the function approaches infinity, negative infinity, x gets very small, the function approaches positive infinity. That means it's increasing. It's actually increasing. Okay. Now, what if n is even? Let's take a look at this scenario where n is even. So we're going to change our dominating term now. The dominating term is now still ax to the n. Remember, that's the leading term. But this time, we're going to make n even. So, for example, we have x squared, x to the 4th, x to the 6th, and so forth. The one I had up here for when n is odd, we have things like x cubed, x 5th, x 7th, like that. Now, when the dominating term has even exponent, again, depending on whether a is positive or negative, as if a is positive, as x gets very large, the function gets very large as well, approaches infinity. And if x gets very small, then the function will still approach infinity because of the even exponent. So for example, if we have x to negative 10 power, remember that's the same as x to the 10 power. So the function is always positive in this case, right? So that means in terms of the graph will stay above the x-axis. So how is this gonna look? Well, for something that has even positive exponent, let's say the function may behave however it does between a given interval, but we're talking about what's going to happen when x gets very large beyond a certain point. So this is the graph. Again, here's the extreme or end behavior that we are referencing here. Let's keep the dominating term the same, but let's change the leading coefficient to a negative. This time, as x goes to infinity, the function should approach negative infinity because now the leading coefficient is negative. Okay? And x approaches negative infinity, the function will stay negative infinity. Okay, so how's this one going to look like? Again, it doesn't matter how the function behaves. Let me actually do this. Let me make the solid line into a dotted line. There you go. Whatever it does here. But when x is very small, and when x is very large. For x very small, this is the extreme behavior. You see that the function approaches negative infinity in both directions. All right, so hopefully we have established this, and these bits and pieces are going to help us graph these functions when it's time to graph them. Okay. Now, let's see how we're going to actually graph these. Okay, so we have reached our fifth objective. Our fifth objective was graphing techniques. Okay. Graphing techniques. So suppose I have a general polynomial again. F of x is a sub n, x to the n. Remember, that's the dominating term when the polynomial is in descending powers of x. And there we have this one. So this is an nth degree polynomial. True? Depending on the leading term. This is an nth degree polynomial. Now, so how are we going to graph this? Well, if you want to graph, this is in general, we'll have specifics in a moment we look at. But our technique is to find the real zeros. The real zeros, remember we talked about real zeros in the previous lecture, section 3.3. If you haven't watched that, please watch my lecture in section 3.3, zeros of polynomial functions. So first we need to find the real zeros. Real zeros translating to the Xintercept, right? Or septs, if there's more than one zero. And we can use the rational zero theorem to do this, right? How do I find the real zeros? We talked about the rational zeros also in the previous section, rational zeros. That's how we're going to find them. And what else do we do when we graph these? We find f at 0. In other words, we find the y-intercept. The y-intercept has points 0 and whatever c. Call it the y component of the y-intercept. Okay, and then of course we talked about the end behavior, right, just now. So we look at the end behavior, and the other thing we look at is whether the graph let me just write out we want to know whether f of x crosses or touches the x-axis. Okay, and that is determined by the power function. If n is even, remember for n even, think about the parabola, how it behaves. The power functions, remember, behave like this. So if n is even, the graph will touch and bounce from the x-intercept. Okay, so that is important to remember. What about if n is odd? If n is odd, the graph will cross its x-intercept. So in the case of n even, it will touch and bounce. In the case where n is odd, it will cross. Now, how it crosses depends on the degree of this of the power function. It could cross like a line does. If it's just x, it crosses like a line. If it's x cubed, then it will cross like actually not quite like a line, but see, it wiggles a little bit. It flattens around 0. There you go. So it crosses like this. As we graph these, I'll point it out through examples how it's going to do it. So there you have it. And also, don't forget, don't lose sight of symmetries. If the function is odd, let me put that. Odd function will be symmetric with respect to the origin. Remember, with respect to a point. And if the function is even, well, even functions, then it would be symmetric WRTO with respect to the even would be symmetric with respect to the y-axis. Okay, so we can always do those tests for symmetries. And again, if you go back to our previous work in our previous lectures, we talked about odd even functions and how to do it. So let's actually do an example together here. In this example, suppose I want to graph this function. I'm going to make one up. Suppose this is 2x cubed plus 5x squared minus x minus 6. Okay, so this is it's not a power function. This is a third degree polynomial function. Okay, so the dominating term here, dominating term is the leading term, right? Is 2x cubed. So dominating term dictates, or it actually tells us about the end or extreme behavior. So the end behavior is going to be exactly like a x cube function. Remember, this is what x cube looked like. So all we care about this is the extreme behavior. So it's going to end up like that for large x, and like this one for small x's. Okay. Now we'll note that on our graph, but let me write it for now. So because dominating term is x cubed, that means as x goes to infinity, f goes to infinity, and as x goes to negative infinity, the function approaches negative infinity. Again, precisely what we're saying on the graph. All right. Now let's see. Let's actually find the things that we said we want to find in here, right here. So we're going to find the zeros, y-intercept. We just talked about the extreme behavior, and then we're going to talk about whether it's going to touch or bounce from the x-intercept. So we need to find the x-intercept first before we can determine that. All right. How do we find the x-intercepts? For x-intercept, we need to solve the equation. We're going to set f of x equals 0. All right. And f of x was that function, the function that you're looking at. So I'm going to let 2x cubed plus 5x squared minus x minus 6 be 0. Now to find the zeros of this, we're going to use the rational 0. Remember P and Q we talked about again in previous section. P, all factors of the constant, plus minus 2, plus minus 3, plus minus 6. Q are the factors of the leading coefficient, plus minus 1, plus minus 2. So the rational zeros is the ratio of plus minus 1. So we're going to take each of these and divide by Q. 1 over 1 is 1, plus minus 1 over 2 is 1/2. Next one, we move to 2. We do exact same thing with plus minus 2. This one, divided by 1, we get plus minus 2. Divided by 2, we get 1, but then I have 1 in my list of rational zeros already. Let's move to 3. Divide 3 by Q, so I get plus minus 3 and plus minus 3/2. And then we move to 6. So here we get plus minus 6 by 1 is 6. 6 divided by 2 is 3, but I already have listed plus minus 3 as my possible rational zeros. And there we have, these are all possible potential zeros, rational zeros. Not all of them can be correct, because this is a third degree polynomial. So we know that this one has at most 3 x-intercepts, which is 3 zeros. Oh, how many turning points? Because it's a third degree, it has 3 minus 1, at most 2 turning points, no more than 2 turning points. Now let's find our first x-intercept. Remember, guess and check, trial and error. So I'm writing the coefficients on the polynomial first of all. All right, and I'm guessing, let's go with 1. Usually we start with 1, -1, 2, -2, and then we move to fractions if those don't work. So let me try 1. 1 times 2, 2, 2 and 5, 7. 1 by 7, 7 minus 1, 6. 1 by 6, 6, 6 minus 6, 0. And there you go. Because the remainder is 0 in synthetic division, therefore we know that x minus 1 is a factor. X minus 1, this is a factor of the polynomial. That means x equal 1 becomes a solution. X minus 1 is a factor, so this would be our first x-intercept. Okay, now I'm down to a quadratic, right? In the third row in the synthetic division table, this quadratic is 2x squared plus 7x plus 6. Okay, if we set this equal to 0, you could go through the list here, okay, and try them and see which one works. Once it's down to a quadratic, we usually solve the quadratic equation by either factoring or quadratic formula. Because if the roots, the solutions are irrational, then this list is not going to help me much. So in a way, it's like I wasted my time, and I still haven't found the zeros because they happen to be irrational, like square root of 2, square root of 7, something like that. So it's a safe bet to solve the quadratic equation rather than trying those other zeros or potential zeros. Now for this one, 2xx, now everything is positive in this expression, so I'm just going to go plus 3 plus 2. I'm thinking FOIL here, so that gives me 2x squared. That's f. F is this one, sorry. This is the O. The O gives me 4x. The I gives me 3x. That's 7x. Good. And the last is 3 by 2, 6. Perfect. It looks like this is going to work. So I'm going to stay with that one. And then we can solve this, right? If we solve this, so I'm going to put here 2x plus 3 is also a factor, which means x is negative 3/2, right? How do we know that? Because you set it equal to 0. And solve for x. Subtract 3, divide by 2, set the other one equal to 0, subtract 2, we get x is negative 2. Therefore, x plus 2 is a factor of the polynomial also. So we have a factor, and here x is equal to negative 2, and we found the other two intercepts. Perfect. So we have the dominating term, extreme behavior. We got the x-intercepts. Oh, how about the y-intercept? The y-intercept is really easy to do, folks. You do f at 0. And when you do f at 0, you just plug in 0 into this polynomial that I have. 2x cubed, 5x squared minus x minus 6. So that one is just going to make it negative 6, right? Because I'm thinking when x is 0, that's 0, 0, 0. I only have negative 6 remaining. And we're good to, I think, we're good to graph this one. So let me grab my coordinate axes. Okay, so there it is. I have my coordinate system here. Remember, the intercepts are at 1, negative 3/2, and negative 2. 1, negative 3/2, negative 2. So let's call that 1, negative 3/2. I'm sorry, 1 would be on this side. In fact, let me make it larger in scale. So let's call that 1. And negative 3/2 would be 1.5. So that's about here. And negative 2 is about here. Trying to space between negative 3/2 and 2 a little bit more. So there we have it. Okay, now let's take a look at our extreme behavior. Oh, f at 0, by the way, is negative 6, right? So that's going to be somewhat down here. There you go. And this is negative 6. Now, one thing that we don't know are the high and low points in this course. Those you get them in calculus classes usually. But for us, let's see how we're going to do this. If I write this in, again, factored form, remember the factored form of f of x is going to be x minus 1, x plus 2, right, and x plus 3/2. All right, or 2x plus 3, yeah, x plus 3/2 is fine, but 2x plus 3. Actually, I like the x plus 3/2 better myself. Yeah, let me do that. I'm going to factor a 2 here. When I factor a 2, I can bring it in front of the multiplication. And indeed, because this way you can see, here's x plus 3/2. Because we can actually see the x-intercept being negative 3/2. Now, every one of these factors repeats only once. The exponent on each of these is 1, correct? So the exponent on x minus 1 here, 1, 1, and 1. Okay, because those exponents are 1. So at every one of these, the graph is going to cross the x-axis. So this is what the cross is. So I don't know. It's just what I don't know is how it's going to cross, right? However, we know the extreme behavior, don't we? We just set it up here. It's going to behave like x cubed, isn't it? Because dominating term is x cubed. And the x cubed For extreme values, x, it points up and it points down like that, right? Remember, x cubed looks like so. We just care about this part and we care about this part. Now, because again, the exponent on every factor is odd and it's 1, so it's going to cross right through it like a line does. Now, I can go through some eliminations. For example, can it cross like this? And the answer is no. The reason, look at the extreme behavior, it's the function is going to infinity, but we just said it has to go to negative infinity. So this is ruled out. If this is ruled out, that means I can X this part out. So we know this part of the graph, it's going to drop like this. All right. Now, the question is, can the function do this? In order for it to do that, it has to come back, right, and go through. But it's not going to do that because we said it's going to go through this point, right? It's going to go through. So this part, this is ruled out, right? There's no way it can be going this way, like that. Therefore, this is ruled out. So at this point, we know that it's going to go up and come back. Good, so we got that part of the graph. How high it goes up, I don't know. Now let's take a look at, this was at -3/2. And then it's got to go through -6, right? So it's going to have to come down, go through -6, and maybe return. Now, whether it exactly turns at -6 or just below -6 like that, or up there, we don't know. Okay, and it doesn't matter in this course unless you want to plot some points. And it would be easy to do. You just choose something like, I don't know, 1/4. It is a fraction, but we got no choice. You can try 1/4 in the function and see if at 1/4 you are below -6 or above it. Okay, I'm just going to make it a return around -6. Now, think about this part of the graph. How can this return and go like that? It cannot. Because here, if it does, then it's bouncing, isn't it? Well, we just said the exponent is odd. X minus 1 has exponent 1. So it has to go through. It cannot bounce. Therefore, bounce is ruled out. This configuration is ruled out. So the only thing that this graph can do is actually come up and go through like this. And it's just going to rapidly rise. So this would be the graph of this function. And again, you can graph it using a software, using a graphing utility, and see how this behaves. Notice in terms of turning points, I have 1, 2 turning points. Again, turning points is the point where the function changes from increasing to decreasing, or from decreasing to increasing. Those are your turning points. And there's clearly 2 of them on this graph. This is a 3rd degree polynomial. It can have at most 2 turning points. Okay, and we are good with this one. Okay, now let's take a look at our next idea here. Actually, before I look at another example, based on what we just talked about in terms of x-intercepts, zeros, and factors, let me just again recap in terms of the zeros and in relation to the solutions and factors in the polynomial. So I'm just going to say that if f is let f be a polynomial function. Suppose I have a polynomial function, and I'm going to let the intercept be at c0. Some intercept. C is a constant, okay? And that is or let's make it an x-intercept of the graph, okay? Of the graph of f of x. So if I have an x-intercept, then the c is also a 0 of the function. Okay, and it's called a 0 because it is a solution to f of x equals 0. So I'm going to write that one. C is a solution. And that was the very definition of zeros of functions. Zeros of functions are numbers that are solutions to the equation or solution of f of x equals 0. And finally, x minus c here can be a factor, is a factor of the polynomial, factor of f of x. So we refer to c in this sense. It plays different roles. It wears different hats. Let's take a look at another example. So in this example, let's say we want to graph, this time I want to graph f of x equals a negative x minus 1, x minus 3, and x plus 2. Let's make that one squared. Notice I made this in factored form. Okay, so it's easier to work with. Right off the bat, we can get the zeros. The zeros are what makes this factor 0, 1. What makes this one 0, 3. And what makes the last one 0 is a negative 2. Those are the zeros, and the zeros are the x-intercepts, right? So I can actually plot these points on the x-axis in a moment. The y-intercept is easy. That's f at 0. So for y-intercept, I get negative 0 minus 1, 0 minus 3, 0 plus 2 squared. That's going to be negative of negative 1, negative 3, and 4. So that makes it negative 12. All right, that's the y-intercept. And then we're going to look at the end behavior. Okay, now the end behavior depends on the dominating term. Okay, for the end behavior. To do the dominating term of this polynomial f of x, here's the leading coefficient. I'm just going to multiply the first x's together. Forget the numbers. We don't want to FOIL them and do all that. If I was to do that, the question is, what would the first term, only the first term would be? So I would be multiplying an x here and an x here, and then x squared out of the binomial times x squared. And then, of course, the whole function f of x would be plus blah, 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 blah. A bunch of other stuff, right? Which we really don't care at this point, because we don't care about in between. We want to know the end behavior. So the first term of this polynomial is going to be negative x to the 4th plus whatever. That would be the dominating term of this polynomial. Okay, now once we have this dominating term, we're going to look at the power function x to the 4th, right? So how is x to the 4th going to behave? Remember, x to the 4th is going to be like a parabola, but only flat around the vertex, around 0 in this case. The function approaches infinity regardless of where x goes. True? And negative in front will cause this to reflect, right? So this would be the reflection. And of course, again, it's flatter than what I had graphed earlier. So there you go. This would be the graph of negative x to the 4th, wouldn't it? So here we're looking at now the extreme behavior of this function. So I'm going to write it. As x approaches infinity, the function approaches negative infinity. As x approaches negative infinity, the function still approaches negative infinity. So it's going to be pointing downward for large values of x. Okay, so there is our extreme behavior. Again, leading coefficient was negative and the degree was 4th degree. Now, near the x-intercepts, near zeros, because the exponent on x plus 2 is 2, right? Because it's 2, so at this intercept, it will touch and bounce, just like a parabola does, a 2nd degree polynomial does. For these other two, because the exponents are 1 each, it will cross. Okay, and now we can transfer this information on our graphs. So let me draw my coordinate system here. All right, So there we have it. I have my coordinate system. I went ahead and plotted the x-intercepts on my coordinate axes. Okay, so remember, the factors were x plus 2 squared. So at that point, it's going to touch and bounce. Now, how it's going to touch and bounce, I don't know, but at -2, that is not 2. At -2, it's going to do this or this. True? At x equal 1, it's going to cross. So it's either going to cross like that or like that. And because it's just x plus 1 to the first power, it's going to cross like a line does. Oops, sorry, it was x minus 1. And the other one was x minus 3 to the first power. So again, at 3 is going to cross exactly like 3, like a line does. And we know the extreme behavior. We just talked about that one. The function is going to have to go down this way, and it has to go down this way. All right, so this part, it cannot touch and bounce like this because it's going in the wrong direction. You see that? It has to come back the other way around. Therefore, it's going to go this way. All right, we got that part of it down. And then it's going to touch and bounce from this. And it's going to go to -12. Call this, I don't know, -12. So it's going to come to -12. And remember, it has to come back here. So it cannot do this. It cannot go forever. Because it's got to go through 1. Through 1. Now, to coming from -12, so it's going to do this. Coming from -12 rules out this possibility, right? Because it's going to have to go through it. If it's going to have to go through it, cuts right through it, like that, then there you have it. That's going to be like this, and it's going to come back. It cannot just keep going like that, because then it's not going in the right direction. It has to approach -infinity. So the only way is to go through this way, which rules out this possibility, right? Now we're just going to make it work like it should. I'm going to make it come back and go through 3. Now exactly how high it goes, it may go up higher and come back and go through 3 like this. There you go. And I don't know what happened to my coordinate axes. Let me just draw them myself. Here's x, and of course the y was like that. Okay, and there we have it. That would be the graph of this function. You're looking at the extreme behaviors, just like it is as a -x to the 4th was. And that is a graph. Now, one thing again, we don't know the peaks and the valley. Is it going to turn exactly at -12, or is it going to go a little bit lower and then bounce back? We don't know. You can plot points and see if indeed it does. Okay, we can plot some additional points. I didn't, but you're welcome to do that. And I'm just going to make this, I don't know what happened. Hold on, let me bring it back. All right, I got it back. So there you have it. And again, the things that we don't know in this course are exact coordinates of the turning points. Okay, we don't know those. The peaks and the valleys, the coordinates, we don't know. The other thing we don't know is where the curvature changes. So for example, it goes up this, comes down, and then in order to go through this low point, because it cannot just stay like that and go through a low point, right? At some point, the curvature has to change so it can actually come back from the trough. So right in here is where that curvature, the measure of bending, how it bends, is going to change in order to make it through the trough. So I'm guessing that point right in the transition point is right in here somewhere, right? This point is called the point of inflection, or simply an inflection point. And again, in this course, we're not interested in inflection points or the max or the minimum of the function. You learn about those in your calculus classes. Okay, and we are good with this one. Now, the other thing, it's going to be really the last thing in this section we want to talk about. It's called the intermediate value theorem. So let me put that theorem and then I'll talk about it. All right, so here it is, the intermediate value theorem. The intermediate value theorem, I've written it for you. It reads, let a function f be a polynomial function with real coefficients. Again, this is important, because if the coefficients are complex, imaginary, this is not necessarily true. But if it is a polynomial with real coefficients, suppose we have two numbers a and b. These a and b are real numbers. If the value of the function f at a and f at b have opposite signs, so one could be positive, the other one negative, the other one positive, then there is at least 1 0 between a and b. Okay, at least 1 0. So for example, this is what in its simplest form this is saying. Here's x, and suppose this is y. Okay, and let me draw this a little more straight. All right, so here I have x, and my y is, let's say, this is my y-axis. And I'm just going to draw this like so. And my a and b are, here's a and here's b. Because the point lies above the x-axis, so f at a is positive. True? The point b, this point at b, lies below the x-axis, so its y value, which is f at b, is going to be negative. Okay, so here's clearly where they have opposite signs. And if they do have opposite signs, right in here, if they have opposite signs, then there has to be at least 1 0. And here is where that 0 is, call it c. See, that's the 0 they're talking about. At least 1. In this case, I have exactly 1. But there are other instances on the graph where I could have more than 1, right? So let's take a look at the case where I could have more than 1 0. So to have more than 1 0, let's say my coordinate system looks like so. Here's my x and this is my y, and this time I'm going to make this go like that. And actually, let me make it go like this, because hold on, my pen is acting up. Okay, so this time I'm going to make it, how about this? There, that should do it. So this is now a, and here is b. This is x, and this point right in here, this is b. And this point, make it a. All right. Now, again, f at a here is positive, f at b is negative. Doesn't matter, f at b could be positive, f at a could be negative, as long as they have opposite signs. But what's important is that you're looking at the x-intercepts. Here I have, how many? I have, I'm sorry, here I have 1, right? Let's count them. I have 1 here, that's C1, 1 here, C2, C3, C4, C5. I have 5 zeros between A and B. So that is why the theorem says at least 1, means 1 or more. Okay? And there we have that one. So we often use this theorem to show that there is a 0 between such and such numbers. Okay, so for example, let me make up an example real quick for this one. In this example, let's see. Let's show if, because I don't know if it does or not, if f of x given by x cubed negative 2x squared minus x plus 1 has a 0 between the interval 2 and 3. So this is A, here's B. Okay, the endpoints of the interval. So for this, we're going to use synthetic division. My synthetic division table is 1, minus 2, negative 1, 1. And I'm going to put 2 here, bring the 1 down. Bring the 1 down. 2 times 1, 2, adds 0. 2 times 0 is 0, minus 1, negative 2, negative 1. Remember the remainder by remainder theorem. The remainder is f at 2, which is negative 1. So we established that. What about f at 3? You can plug it in directly. I rather just use synthetic division here. But here's how you could do this, by the way. With f at 3, this isn't bad, but sometimes it can save you time in doing this. There. That's f at 3. So this is going to be 27 minus 18 minus 3 plus 1. And all said and done, this should be 7. Okay. Or you can use synthetic division. Now the point being this. F at 3 is positive. F at 2 turned out to be negative 1 less than 0. These have opposite signs. Because they have opposite signs, then that means there is at least 1 0. 1 0 in the interval from 2 to 3 for this graph. Okay, so we have established that. All right. So now we're done pretty much with the lecture portion. We just have to do some, maybe a few exercises here. Not too many, but we're only at 1 hour into this video lecture. So let's actually try something like, let me try an example here in the exercises. I'm looking at actually a page of a book here. And let's see if I can do this one. Let's say in this example, we want to look at the end behavior. That's it. F of x is negative 4x cubed plus 3x squared minus 1. Okay, we want to describe end behavior of this function. Okay, so to describe it, we look at the leading term, right? So the dominating term is negative 4x cubed. Forget everything else, the other two terms, we just focus on that one. So this is going to behave like x cubed does, right? This is how x cubed behaves. Right? But the negative in front will reflect this, doesn't it? So this is actually the true behavior we're looking for. These are the extreme behaviors. As x goes to infinity, the function goes to negative infinity. That's for x getting large. As x goes to negative infinity, the function approaches infinity. That's for x getting very small. You see that? So that's how we determine the end behavior. Okay, next let's graph a function. So in this next example, let's say my f of x is 2x cubed. Then we have x squared minus 4 times x minus 1. Now if the function is factorable, if each of these factors themselves are factorable, we need to do that. And the reason I say it, because this x squared minus 4, difference of two squares, that is factorable itself. We need to factor this as much as possible so we can do this correctly. Okay, so for this one, let's see. The dominating term, first of all, dominating term is going to be the first term in the polynomial. To get the first term, you multiply x, and x cubed. X cubed times x times x. 1, 2, 3 x's. And then a 2 in front. That's important, the leading coefficient. Because if it's negative, it's going to flip the graph, right? So the end behavior will be different. So the dominating term seems to be 2x to the 6th power, right? 1, 1, 1, and 3 makes 6. Therefore, the polynomial function we look at here, in other words, is a 6-degree polynomial. Now, that means the extreme or end behavior is going to be like x to the 6. Now, remember, x to the 6 is a power function and even. This is how x to the 6 will look like. And these are the extreme behaviors. So as x goes to infinity, and the coefficient, by the way, leading coefficient is positive, so that's not going to influence the arrows. The graph is not going to reflect. It's not going to flip over. So as x goes to infinity, the function goes to infinity, and x goes to negative infinity, still goes to infinity. Right? Here's infinity here, infinity here. All right, so we determine the extreme behavior, and that's good. So next we're going to look at some of the other basic stuff that we're looking at, like the intercepts and so on and so forth, right? The x-intercept. Those are the zeros of the function. X is 0, that comes from this one. X equal -2 coming from that one. X equals 2 coming from that, and x equals 1 coming from this one. So the graph of this function actually has 1, 2, 3, 4 x-intercepts. That's very good, interesting. 4 x-intercepts. Let's look at turning points. How many turning points? Turning points, this is a 6 degrees, so it has at most 5. That would be 6 minus 1. At most 5 turning points. Okay, we got the x-intercepts. Let's do the y-intercept. For y-intercept, we do f at 0. That's 2 times 0 cubed times 0 plus 2. And because this is 0, pretty much everything is going to multiply to 0 here. Doesn't matter what these other numbers are. So that's going to be 0. And if x is 0, typically that's the sign that y is also 0. Because remember, these are x-intercepts. The coordinates are 0, 0, -2, 0. At x-intercept, the y is always 0. And there's your y-intercept right there. So if x is 0, y is also 0, but I just showed you that. The y-intercept is at 0, 0, the origin. And what else? I think that's all we need. Now we can actually go and graph this one. Here's my number line. This is x. And I have, this is the y-axis. We know the extreme behavior, right? It's going to go like this. Now, each of these factors repeat one time except x cubed. See how x cubed? This is a 0 multiplicity of 3. So x cubed is going to behave at 0. That's when x cubed is. So I have 0. Let me first locate my intercepts. That's -2. This one is 2, and this one is 1. Okay. Because 0, x equals 0, has multiplicity of 3. So it's going to, the odd exponent tells me it's going to go through 0, right? But it's not going to go through like a line does. It's going to go through because of x cubed. It's going to go like this or like this. The other choice is going this way or that way. See how it wiggles around 0? It doesn't, it goes through, but not exactly like a line does. It doesn't go like that. Okay, the others have multiplicity of 1. This one, this one, this one. So at these other intercepts, it's just going to cut right through it without spending any time. So it's going to cut through, coming from here, it's going to go through this way. So this rules out this possibility. Okay. And then in order to go through this 0, it has to come back, right? It cannot just keep going like this. It has to come back in order to go through this 0. And so it's going to go up, and then it's going to come back. It's going to wiggle a little bit, and then it's going to go wiggle the other side, and it's going to go this way. That rules out this possibility, right? This one is ruled out. Okay, and we're going to erase that part. Now, it's going to go through 1, correct? And through 2. So the only way you can do it is if it does the following. it's gonna have to, so it's gonna go like this, and then it's gonna turn, go above, and cut through in order to do the ladder part. And there you have it. So that would be sort of the graph of this one, except let me see. Oh, it has to be, sorry, the end behavior was, see, I didn't graph it right. This is the end behavior. We just set it up here. No worries, we'll fix it real quick. Therefore, the graph's gonna come through here. It's gonna have to bounce, go through this, come back here, and cut through. There. And again, the reason it wiggles here is because you have x cubed at that point. Sorry about this. I don't know what happened. All right. Sorry about that. I was able to redraw it. So here we have it. And that would be the graph of this one. Again, notice because of x cubed, there's a wiggle at 0. Otherwise, at 1, it cuts right through it. Right? You see that? It cuts right through, comes back, cuts right through. It's not going to wiggle at these points. It will just go straight through. And there is the graph of this one. Okay. And I think we are good. We've done enough examples on this one. So hopefully this will help you graphing polynomial functions. It will help you to graph them. Remember, the end behavior is really the key here. The extreme behavior or end behavior of the function helps us a great deal. The power functions were great use to us. The general form of x squared, x4, x6, x cubed, x fifth, and so on. So we are done with this lecture, and as always, again, thank you for watching.